Ladies and gentlemen, today's gentle conversation deals with the subject of geology, and we're going to start out here. I've got a little picture. This is a amphitheater just west of Denver called Red Rocks. You might have heard of it. I think it's an interesting picture. You can see a little bit of the amphitheater there. It has nothing to do with anything, but this geologic formation right here, you can see that there's kind of a layer structure going to it, but that the layers are tilted sideways. And so the reason I like this picture is that, one, Denver's a nice place, but two, a lot of interesting things going on with the rock here. You can see how they were laid down, but then the whole earth is shifted, is tilted, has uplifted that piece right there. So just kind of a testament to some of the incredible forces that are going on in geology. Let me show you some minerals here. Minerals are simply the building blocks of rocks. And so here you see little strings that can be made with these minerals. These are all silicates here, which is a particular mineral. Silicate has a silicon atom, and it's surrounded by 4 oxygen atoms, so it makes like a little pyramid, a little 3-sided pyramid thing. There's a nice picture in your book on page 273, but you can see these little pyramids. Here's one from straight above. These things still are missing electrons, so they're looking to make covalent bonds with other silicates or whatever else they find. Here, for example, 2 of them have tied together on that corner point, and that's what they refer to as a bow tie silicate. If you get 6 of them in a ring, it's a ring silicate. Here's a chain of them. They go this way. Framework, they can lay out in big sheets. Double chain silicates, where they get a chain coming this way and a second one tied onto it. Looks a lot like the sheet, but it would only be two columns wide. So, lots of things can happen here. You've got lots of other minerals, of course. This is just one example, but look at the different shapes and colors and geometries and morphologies here that can come out of these silicates. These crystals, here's amethyst, which is a quartz crystal. So it's a regular silicate composed material, but it's got purple that's seeped in from groundwater or other things that make it that way. Here's a rose color, amber color, yellow. There's just a lot of variation that can go on in these minerals. Again, the minerals make the rocks, so if there's variation in the minerals, then there's going to be variation in the rocks that are composed out of those minerals as well. So lots of things can happen. It's very exciting, I tell you what. Right here, the first kind of rock that I want to talk about is an igneous rock, and igneous means out of the fire. So this is a rock that was molten at one point. It was liquid goo. It had melted down, like if you took wax and you melted the wax and then you dripped it on the countertop and it cooled and solidified. It'd be the same idea here. You'd have to get a rock a lot hotter, of course, and it would take longer to cool off, and it would burn a hole in your countertop. But here you see some igneous rocks. This glassy, shiny black rock here is called obsidian. You've got granite and all sorts of these things, but they were all molten. It was liquid, and then it cooled off. Maybe that was due to a volcano, right? You've got the magma deep in the earth, and it comes up, and when it erupts, then it's called lava. And if it cools very, very quickly, you get a glassy black rock, like if it fell into water or something. If it was trapped underground and cooled off over a very long time, you'd get something totally different. So again, the process determines everything. Right here above this black line, you see some minerals that make up igneous rocks. All right. Some of these you've probably heard of. Quartz, for example. Some of them you might not have. Muscovite, K-spar, olivine, pyroxene. Lots of stuff here. Lots of choices, options. Below this black line, I've got some examples of igneous rocks. So here, for example, is granite. Here's another granite. They don't even really look alike, right? I mean, they're both kind of splotchy and whatnot, but again, the minerals that grow into it determine what it's going to look like. And so if you had some pinkish minerals, and you end up with pink granite. Here in the state of South Carolina, we have blue granite. And it just, depends on what the process was and what went into it. Here's basalt, and you've probably heard of, there's obsidian again, that glassy black rock. You might have heard of pumice. That's a real rough but lightweight rock. Scoria, let's see the little bubbles in it. Again, a volcanic rock there, and those bubbles were air bubbles that got trapped in there as it cooled. Lots of things can happen. All right. The second kind of rock is sedimentary rock. Right here you see that it says rocks are formed by layers of sediment being compacted and cemented. Very simply, sediment is any kind of material that washes. Could be sand, it could be silt, it could be little pebbles, it could be anything that's going to wash down from the mountains or a canyon or something and get picked up by the moving water typically, and then carried somewhere else, deposited. It gets built up in layers, and as that gets compacted together, then it can be cemented and form a rock. These rocks are not as strong as the igneous rocks because it's just a bunch of sand glued together. All right, right here, for example, sandstone. You can take sandstone in your hand, you can kind of rub it, and pieces of sand start flaking off onto your hand. Here's limestone, and that's a little stronger rock, but not a whole lot. All of the caverns and canyons here in that people like to go to, those are limestone, and the water moving through under the mountains carved those canyons over thousands of years, millions of years, and because the limestone was softer than the rock around it. Here's shale. Conglomerate is a sedimentary rock with just a whole bunch of weird stuff thrown together, compacted and cemented. So it would have little pebbles in it, and it might have other stuff that you might not see. Gypsum's an interesting sedimentary rock. Again, layers of stuff built up and then compacted and cemented. I've got some examples here that you can do, right? Limestone, coal, chalk. Chalk is a sedimentary rock. Coal is an interesting sedimentary rock right here because it burns, right? In addition to all the sediment, the sand and the silt and whatever else, it also had organic material. So leaves and plants and stuff got compacted in there, and that energy is still in there waiting for us to dig it up and burn it. So that's interesting stuff. Could you pick a favorite sedimentary rock here? If somebody snuck up to you in a dark alley and pointed a gun at you and said, "Quick, what's a sedimentary rock?" Could you think of one? I'd like you to know at least one example of a sedimentary rock, at least one example of a igneous rock. Here are those again with the right here. So pick you one of these. Granite would be an easy igneous rock to remember, or obsidian, whichever. All right, but just kind of have a pet rock here. Have one of each. There's an igneous. Here's the sedimentaries, and then we've got one more kind I haven't told you about yet. That's called metamorphic rocks. A metamorphic rock here is one that has been changed into a new form. It's been changed. What changed it? The heat and pressure deep in the earth. If you look at this picture over here, you can see that there's a magma chamber. That, of course, is liquid rock. It's melted. It's goo, and that's got a lot of heat going on. All these piles of rock, all these layers, tons and tons and tons of earth are pressing down on everything inside. So this rock right here is getting the heat from the magma chamber, and it's also got all this weight pushing it down, and that's going to change the rock. That's part of the process that happened to that little piece of rock, and that heat and the pressure change it. They cause a metamorphosis. They change it into a new form. They bake it, if you will. If you take, for example, granite, and you expose it to tremendous heat and pressure deep in the earth, you end up with schist, right? If you take shale, not shale, dadgummit, take, oh phooey, I lost my brain. Sorry. I give up. Sedimentary rocks may become metamorphic rocks, and igneous rocks may become metamorphic rocks. Right here, limestone turns into marble. All right, marble is much harder than the limestone. All the the classic statues and stuff that we see from Greece and whatnot, those are carved from marble because it's a very hard, durable rock. But so they've got those properties. Here again, the minerals that go into metamorphic rocks, they're the same ones that went into sedimentary and igneous rocks, right? Down below, you've got some examples. Pick out one of these that you like too. Marble would be easy to keep up with. Here is slate. So whatever you like. All right, one of each. I got a little picture here that tries to kind of illustrate this. This is sometimes called the rock cycle for obvious reasons. A whole bunch of arrows and stuff. It's not really the arrows that, right here you got your igneous rocks, and here's the sedimentary rocks, and here are the metamorphic rocks. And the idea with this picture is it kind of shows you how all these transitions occur. So, for example, if we started with an igneous rock, weathering and erosion could break that down into sediment. The sediment could be washed downstream, it could be dropped somewhere, and that as it got layered up, as it got piled on, then it would get compacted and cemented together, which would make it a sedimentary rock. If that got buried deep enough, the heat and pressure could turn it into a metamorphic rock. It could weather and erode back into sediment and become a sedimentary rock, which could be changed to a metamorphic rock. That could melt and turn into magma. When that cooled, it would be an igneous rock, which heat and pressure. You get the idea, right? You can just, the process is what determines what the end result is. When you pick up a rock, it's had at least one set of these conditions, either compacting and cementing, heat and pressure, or cooling into a rock. But these things go around and around, and can change form. All right. Some rocks have this natural structure to them, this layer. If we were to zoom in and look at the atomic structure, the molecular structure, here, can you see that these molecules are bound together by bonds? And some of these bonds are stronger than others. Right here, maybe along this red line. Maybe that bond's weaker than these where they're closer together along the yellow line. So if you knew what you were doing, you could break it or cut it along that red dotted line right there. And you can see here where there's a razor blade stuck down into this rock along the cleavage plane, which is what we call this. There's a space where it will easily break and form up into a new shape, if you will. Right here you see some rough, old, ugly rocks, right? They're kind of glassy, kind of look like melted plastic or something, and people have cut them and worked them into these sapphires. Well, these were sapphires too. They were just rough sapphires. But as we learn about the cleavage planes and where to strike these things, with a chisel kind of thing, or to polish them on a grinder, then we can shape these things into jewelry and whatnot. So that's an interesting aspect of geology as well. All right, we'll be back in just a little bit here. Welcome back. Here in Chapter 38, we're talking about erosion and sedimentation. We've kind of mentioned those terms before. Erosion, of course, is the breaking apart of rocks and the washing away of material. Sedimentation is where that material is relayered, is dropped off, and it piles up somewhere. So let's take a look at some pictures here. This first picture here shows kind of two things that are going on. Right here you see a fast-moving creek, and that fast-moving creek is cutting the land out, right? The moving water picks up little sand and rock and whatnot and carries it downstream. You can see the banks of this thing have been cut down in, and the creek is lower than the land up here. All right. If you go down to the Catawba River, you see that the banks are cut out. It might be 6, 8, 10 feet from the land down to where the water level is. It's been carved out like that. Right here, the is a picture of the slow water. So the Catawba River goes around a bend, and on one side, the outside side, you get a bunch of sand and sandbars and mud and stuff that's washed out, and it's dropped there. As the water slows down, it's not carrying that rock anymore, and so it just drops it right there, and it'll pile up like you see here. If enough of that piles up, then you get compaction and can get cementation in a very long process. Okay, here's a picture of some erosion or weathering. This you might see out west somewhere. You can see that the land once ran all the way across there, right? And this has just been cut out. What forces would remove that much rock? Well, you got the wind, you got water, you got ice, right? If there's a little crack in the rock and water runs down into the crack and then it freezes, when water freezes it expands, and so that's going to push on the rock and break it loose right there. And lots of forces can over thousands, millions of years reshape, carve out the land here and just leave these pieces. When I look at this picture, do you see the layers running there? Those layers tell me that this was sedimentary rock. I know that sedimentary rock is not as strong as the other two types of rock, so you can see that this would cut out quicker than if it were something else. The picture may not show it very well. Excuse me. But down here you see that there's kind of piles of stuff. That is the sediment that's been removed right there. Some of it's already been carried downstream and deposited somewhere else, and it's working on its cycle of whatever. A couple pictures from the air here. This is the mouth of the Mississippi River, and as it slows down and moves into the Gulf of Mexico, can you see all that sand that is dropped, and it forms all these sandbars. Those sandbars shift and move over time, but that triangle there, the Greek letter that looks like a triangle, is a delta. So we talk about the Mississippi Delta, and that's that region right there. This is called a fan. Picture's not real clear, but here's a big mountain. Stuff is washing down from the mountain, and it gets in this little valley, and it runs, and then as it slows down here, it drops that, and it fans out around this region here. An alluvial fan is the big fancy name for that, and they talk about that on page 281, so you can go find that. The wind and the waves remove material. Right here's a picture of a kind of dry area, desert area, and you can see that the wind has just blown material away, except where there's a little plant there. What's so special about the plant? Every one of these little high places has a little plant on it. The plant has a root structure which reaches down into the soil and holds on to that little bit of soil so that it doesn't blow away or wash away. If you go to the beach, you know that they get real excited about the sea oats that grow on the sand dunes, right? If you get caught cutting those, it's a big fine and big trouble, so don't do it. That's because the roots hold that sand dune together, and then if there's a storm, if there's a hurricane, whatever, that sand dune's not going to wash away, and maybe the houses behind it have a little bit of shelter from the sand dune. Here's an interesting picture again from out west somewhere, California or whatever. You can see that this mountain comes down like this. Here's the ocean, and the ocean waves have been beating on this mountain for millions of years, and they have succeeded in beating a hole through this one. There's a little tunnel kind of thing cut by the waves slapping on the rocks over and over and over and over again. Yep. All right. Chapter 39 deals with volcanism, which would be volcanoes, and diastrophism, which would be the moving of bits of earth. So let's take the earthquakes and the like. So looking at volcanoes here, you can see that again, down deep in the earth, it's molten, right? We've got this magma that's built up there down in the outer core. I'll show you a picture of the layers of the earth in just a little bit. But you've got magma, which we call lava, as soon as it erupts up here. But if it can find a crack, remember this is under a lot of pressure. It's being pushed, and so if it finds a way to the surface, it's going to take it, right? And these things, these volcanoes may lie dormant for 100 years, and then something gets them excited, and they erupt again. Sometimes they'll find little side cracks and run up to the side. Right here's a big magma chamber right here. Big burst of pressure could push that out and just blow out the whole side of the mountain here. That's exactly what happened with Mount St. Helens. It's a volcano, active volcano out in Washington State, and I've got some pictures of that in just a second. But before we do that, let's point to some of these terms here. The magma chamber is here. This line running right here is called the central vent. And that central vent would carry magma to the surface. Generally there's a crater here. If it erupts, then it's going to kind of blow material up into the air. You see here that there's some ash and rock that's shot up into the air with these eruptions. That's going to leave a little divot right there, a little crater. And of course you got material that's coming out of the top of the volcano. That's going to fall down and spreads out over quite a large area, but most of it's going to fall on the surface of the volcano here, which is going to kind of build this thing up in layers. And so you can see here the strata, the layers of this thing. Every time it erupts, you're going to get another layer built on top of the thing. And so the volcano has the potential to get taller and taller, bigger and bigger, because every time it erupts, it's depositing more mass and more rock and whatnot on top. It also has the potential to get smaller. If this eruption is violent enough, then it can take all this material and blast it up into the air, and it goes somewhere else. So these things change over time. Here's some pictures of Mount St. Helens. This was in 1980. I'm old enough to remember this when the thing went off. Here's a picture beforehand of Mount St. Helens, and you can see the crater up there, a little bit of smoke and whatnot. And these pictures take place over, I don't remember, 45 seconds or something. I mean, this was a long, but they happen one right after another. Right here you can see in this one that the eruption is beginning. It's not really so much up here in the crater, it's more on the side, isn't it? And you see that this eruption is coming here. This big ash plume just flowed out, and it stretched hundreds of miles. I mean, the ash was just deposited everywhere. There was a light sprinkling in Columbia, South Carolina, where I was living at the time. Huge amount of energy was released here, equal to 10 million tons of dynamite going off. 63 people were killed. Most of those were people that wanted to see the volcano. This is always something people want to see. Oh, I want to see the volcano. So they pack a picnic and they go out there and sit in the forest which surrounded Mount St. Helens, and they were a little too close. So, or they didn't listen to the warning, get out, kind of thing. $1 billion of damage. That was in 1980 dollars. There were 200 homes that were destroyed. 185 miles, I should say, square miles were just destroyed. You see the woods here, the trees. Acres, hundreds of acres were just blown down like matchsticks from the force of this thing, and from the mudslides that followed, and just everything that went on. So pretty interesting stuff. We don't really have a volcano right around here, and that's okay with me. Here's an interesting place. You can go to this down just east of Atlanta, Georgia. It's called Stone Mountain, and there's this big rock, big massive rock. Those are trees on the very top of it. There's a building on top, a little visitor center. There's a cable car that runs up to the top if you're too lazy to walk up there. Somebody got the bright idea to carve on it, and so you can see that too if you want. But this is all one big rock. It's a big pebble, right? It's an igneous rock, and here's what happened. If the magma chamber found a vent that went up, then all this magma could flow up into this region here. But if it were trapped there, then it would just sit there, and gradually it would cool off and turn into an igneous rock. Later, all these layers of dirt and stuff were removed by erosion, by sedimentation, and so this covering was washed away, and we're left with this pretty good sized rock to look at and climb up and do whatever. There's another one of these here closer down in Lancaster. There's a place called 40 Acre Rock, and you can look it up on the internet and go walk out there. Real nice day hike. It's about 2 miles in, 2 miles out, something like that. Real nice walk. You should go down there. But you can only see the top of the thing. There's a big flat rock, and it's one of these things, but it hasn't removed all the layers yet. We're kind of down along, it's washed down to about here. Another 100 million years, you could come back, it'd probably look like this. It wouldn't have the little carving thing yet, unless somebody got busy on it. All right. Faults. These are interesting. Again, these are mostly out west. There's a big one called the San Andreas Fault. You've probably heard of that. And essentially it's a crack in the earth, and the two different pieces, this side and the other side, are moving relative to each other. And now sometimes one piece moves up and the other piece moves down. It's called a normal fault. This is kind of the same thing. This one's moving. Here you can see that there's also some movement west and east, which are going to separate those two and pull this down. Here, if they're moving towards each other, it's a thrust fault, and that's going to push one layer up over the other one. So you get a little overhang kind of thing going on there. The strike slip fault, you've got one piece that's moving south and the other piece moving north. And so these things are sliding against each other. But this is a picture of the San Andreas Fault. Here's a region here. You can see the roadway, and the fault moved, and the yellow line doesn't run straight anymore, right? It jumps over a couple feet. That's okay. You can come back and repave it, and you got to pack it and all that. But what if there had been a gas line or telephone lines or sewer lines or something running through there? You can see there's a lot of potential for destruction here with shifting faults. Earthquakes tie into those really nicely. Fault lines run, and that's where the earth is moving against each other. If a tremendous pressure builds up and then is released, that causes vibration, shaking, earthquakes, and the damage from earthquakes can be astounding. Right here, this is a picture of a seismic wave. When you think about the earth moving and this vibration that's released, then the thing can either shake back and forth this way. We call that a compressional wave or a P wave. It can also shake up and down. You can see that this earth is vibrating up and down. So it's either side to side, compressional wave, P wave, primary wave. It's shaking up and down, shear wave or S wave, which also stands for secondary wave. Turns out these kind of waves travel faster, and so they always get out ahead of these kinds of waves. And that's interesting, because what we can do is we can build a little device. It's essentially a ballpoint pen, and there's a moving piece of paper here. If you drag this piece of paper to the side, if it's a nice calm day, you're going to get a straight line, right? But if the earth shakes underneath you, then it's going to get this jaggedy line right here. And we call this a seismograph. It's going to draw a picture of the seismic activity going on, if there's any earthquakes going on. Here's North America, and there's a little seismograph station right there. Here's South America. They've got a seismograph station. Europe's got one, looks like on England here. And all three guys are listening, and they'll go, "Whoa, felt an earthquake." And so North America here says, they do a little calculation I'm going to show you in just a second. And they say, we know the earthquake happened 2,800 kilometers away from us. And South America radios in, we got 3,400. And so you draw those two circles, and you can see that there's two possible points right here or right here where those two circles cross. And so it had to happen in one of those two places. If you can get a third station right here, Europe calls up, says 4,800. You draw that circle, all three circles cross right there. That would have been the epicenter of the earthquake. How do they get these numbers, 2,800, 4,800? Let me show you real quick here. This is what the seismograph might have looked like. And you can see that here's a nice calm day. Everything's just ticking along. And all of a sudden, right, there's that P wave, the primary wave. It's hitting right there. And they've gone ahead and set time to 0 when the P wave hits. And it vibrates, and the P wave dies out right about there. About that same time, the S wave, the secondary wave, the up and down force hits, and you can see that that's even more violent. more active there. How do you know? Because it's shaking it farther away. Right here, this thing went up, this is about as high as it got. Look at this S wave, it's even higher, and that's typical. The P wave is smaller, but it travels faster. Secondary wave is more violent and can typically last a little longer. So here comes the S wave like that. There's two numbers that you want to get off of this seismograph if you're trying to do these calculations, and you will be doing these calculations, so listen up. You want to know how long it took from the beginning of the primary wave to the beginning of the secondary wave. That's called the SP interval, the PS interval, whatever. All right, get that time. Since these all start at 0, all you really got to do is look right here, see where the S wave hits, come straight down, and get the time. So that'd be like 36 seconds there. All right. You also want to know the amplitude. The amplitude is the maximum height away from the center line. So a nice calm day runs right here, and you can see that this one shook all the way up to here. Now these are in millimeters, but if you follow it over to the y-axis there, that would be what, somewhere between 150 and 200, and we'll say 180. All right. So my SP interval is 36 seconds. My amplitude is 180 millimeters. Now I would write those two numbers down. Now remember, we said that in order to do this you got to have 3 different stations. So here's some actual earthquake data from an earthquake that I remember. Some of y'all might remember it too. And let's take a look at it real quick. Eureka, California is right here. They felt the wave. Here's the beginning of the P wave. Here's the beginning of the secondary wave. If you drop down, you see that's 50 seconds, so they wrote that number down. I need the amplitude. That's the maximum height. Would be this number. Happens to be covered up, so I'm going to use the bottom one here. Something like 280. All right. So I'd write that number down. Las Vegas does the same thing. Here's the P wave. It dies out, and then the secondary wave hits. Again, it's higher, bigger, stronger, longer. And write down the 64 seconds right here from the beginning of this one to the beginning of that one. The amplitude looks like it's about 100. Write those two down. Elko, Nevada, that's way up here. And you can see they felt a little bitty thing here, and that died out, and then they felt a secondary wave that went there. So 72 seconds, amplitude's only 60. These guys felt it the strongest, 280 on the amplitude. These guys felt it the weakest, 60. So doesn't that kind of indicate that the thing happened somewhere closer to Eureka than Elko? You know, if we kind of drew a line between those two, we'd expect it to be more on this side over here because the amplitude was so much stronger. Also look at the time. 50 seconds on the PS interval, 72 seconds over here. So it took less time for that secondary wave to come through to Eureka than it did over here to Elko. So all 3 of these would do their calculation. Here's the calculation they would do. They'd use a chart like this, and you'd come up to, well, we said Eureka was 50 seconds. So all you got to do is you come up on this chart, there's 50 seconds, go straight across like that until you hit the diagonal line, and then just drop straight down. And that'll give you the distance in kilometers. See, that's a little bit shy of 500 kilometers. 488 is what comes out of that. Elko was 72 seconds. Come way up here, Elko. Go over 72, hit the diagonal line, drop straight down, and we're just shy of 700 this time. So that's how they're getting those distances to find the epicenter. All 3 of these guys would draw the circle, and here are the circles. Eureka's California is shown. Eureka's circle is shown in blue, runs somewhere like that. Elko, Nevada is the red circle, and you can already see those two cross right there. They also cross up here just off of the map, but can't see that. But when Las Vegas nails it down here with the green circle, you see that all 3 circles cross right there just south of San Francisco, and this indeed is where the center of that earthquake was. If you want to create a gauge to say how strong it was, you use a chart like this. You'd need the distance and you need the amplitude. Remember, we've got those 2 numbers. We calculated the distance off of that other chart with the diagonal line. This one came off of the seismograph. So right here, Elko No, I think Eureka, California was the blue one, and 495 or something was 488. I think was the distance we worked out. The amplitude was 180, so I want to get 488 on this side. I want to get 280 right here, and I just draw a straight line between the two, and those are going to cross right there at about 7.1. All right. Las Vegas does it, Elko, Nevada does it. They all cross at the same place. That is the magnitude. You hear this referred to as the Richter scale. It's a logarithmic scale, and so every time you go up from 4 to 5 or 5 to 6 or something, it's getting 10 times worse. It's a stronger earthquake, and so a 7 is a pretty heavy-duty earthquake. That's on the upper end of the scale there. I've got some pictures from this earthquake, so let me show you that real quick. Right here, this was the Loma Prieta earthquake. It was in 1989. 62 people were killed, 3,000 were injured, $7 billion in damage. We've had some big earthquakes here lately. Haiti was a terrible thing, and India had a big one. China had a huge one. These things hit all around. Here you can see some highway bridges, and pieces of them fell out, right? And here's tangles of buildings and stuff. Here's a bridgeway out in San Francisco. They had bridges built on top of the bridges, and so when the top bridge fell, it trapped cars in the middle, and they worked for days to get people out and stuff. These people have a nice new canyon in their front yard, so all sorts of things can happen here. I got one more picture, and we'll take another little short break here. But these are the layers of the earth. The reason I wanted to put it with this is because if you look at the earthquake data, that's how we get this information about the layers of the earth. I've got a crust here, right? The outer surface is referred to as the crust, layer D. Inside that I have a mantle. That's solid rock, but it's got some magma flowing through it and whatnot. This yellow layer here, light yellow, is called the outer core. That is liquid. It's molten rock. So everything's kind of floating on this molten rock here. And then down the egg yolk here, if you will, is the inner core. It's a solid metal. And so that's the structure of the earth. Everything that we know about is the crust. And the numbers are there in page 298. If you want to go look at the thicknesses of those layers, there's a nice description there. All right. Let's take another little break here. All right, this last little bit, just got a couple things left for you here. Right here, we're looking at a map, and Chapter 41 talks about this, but there are plates. There are pieces of earth that are kind of separate from each other. We're all floating on the magma here, and the mantle and the crust kind of floating on this magma, and as such, these things can kind of move around. And here you see North America, and we sit on the North American plate, which runs right here. So it's all one big piece of land, but then there's a separate piece of land for the South American plate, and the Nazca plates right here. The Pacific Ocean sits over the Pacific plate. The Indo-Australian plates over here. You got the idea? There's these pieces of land, and they kind of bump up against each other, and they move. If you notice the fault lines, there's the San Andreas Fault, runs right along one of these plate lines. If you notice the volcanoes and the earthquakes, these red dots, kind of mark those, they run right along these plate lines. And so anywhere that you have this land that's bumping up against each other, you're more likely to get earthquakes because there's movement there. You're also more likely to get volcanoes because there's a crack, right? And magma can find its way to the surface, and so these plates are pretty important, especially in certain areas. Japan and China over here, they've got a lot of that stuff going on. Okay, the ocean floors have a real interesting geology, just as interesting as the mountain ranges and stuff. Here's the Appalachian Mountains in the United States, right? but here's a big mountain range. Or some of these are formed from these land masses moving away and stretching out, making canyons and caverns, or maybe they're pushing towards each other, and stuff's being uplifted and moved together. And so that's good stuff. The plates, if you looked at them from the side, would look kind of like this. You can see there, this might be the Pacific plate right here with the Pacific Ocean underneath, and then the land mass here is kind of riding up and over the Pacific plate. Here's California and the mountains, but there's all those fault lines and volcanoes jumping around in there. Out here and so one way you can get mountains is when this plate and bumps up against this plate, then you see how all the rock is kind of wrinkled up right there. If you put your knuckles together and push with the hands, see how eventually your arms have to push up, and that uplifting is referred to as mountain building. Orogeny is the fancy word. The other thing that can happen is one plate can slide up and over the other plate, and that's called subduction. Here you see it labeled subduction zone, this place where it's pushed underneath and this other one's riding up over the top of it right here. So that's one way that mountains can get built, when these plates slide into each other very, very slowly. Centimeter a year or something like that. I don't remember the exact number, but very, very slow movement. Right here's the second way the mountains can be built. If you have a vent that comes up and forms a volcano. Now this one's underneath the ocean, so you wouldn't see anything, and then all of a sudden, boop, a little island pops up, right? As the strata, as the layers of the volcano build up, every time it erupts, more materials deposited there on the cone of the volcano, and it builds up, and eventually it pops through the surface. The Hawaiian Islands, for example, those are all volcanic islands, and they were formed in this way. And as those fault lines move, see the vent might have been right there and made a little island, and now the vent's over here making this island. As things move, then you get a little string of islands like the Hawaiian Islands that were formed up. These plates, we said, move. Check this out right here. In the animation, you can see that the animation, which isn't working at the moment. Ha! That's interesting. This animation shows how these plates move together. You've probably noticed and read about how the contour of North and South America fit so nicely up into Europe and Africa here, and these were originally all one land mass, and the things have moved away from each other. And so that's something that they're still studying and learning about. There's another guy now, he says, well, the backsides fit too, but that means you had to have a smaller Earth. So here's a new theory coming out. Are we going to just, you can do a Google search on growing Earth theory, and there's a nice animation there about his thing is, well, if the Earth started out half the size and it swells out, you'd get exactly what you see now. Are we going to embrace this new theory with open arms? Not quite yet, because there's a lot of things that have to be explained. Where did all that extra mass come from, and what does that do to the heat of the Earth and everything else? Is it interesting? Yeah, it's interesting. Is it something worth looking into? Absolutely. And so if you want to take a look at that video, Growing Earth Theory, that's another alternative view of the beginnings of the Earth. There's some nice things about it. There's some unanswered questions too. So science moves along slowly, and we're cautious, we're careful, we're interested in new ideas, but we want to make sure that we don't jump off a cliff somewhere and do something hasty. So that's about it. That's what I know about geology, and thank you much.